Hello, everyone, and thank you for taking the time to watch our presentation about our research ALD system. This system is built in collaboration between Maxima Sciences and GP Plasma. This presentation was first given at the 2022 TechCon for the Society of Vacuum Coaters in Long Beach, California. To give you a little background on ALD, if you're new to ALD, I wanted to share this timeline. So ALD is often referred to as a very young technology in the vacuum coating world, but it's been around a fair number of years. The first references to atomic layer epitaxy appeared in 1965, but there was a fair gap between when the technology was identified and first research began in it and when it was used in an industrial process, the first pilot production plant showing up in 1983. Plasma enhanced ALD came along several years later, but again, a large gap followed by spatial ALD, and then a significant gap followed by area selective ALD in 2016. So while this work was done by quite a few folks and by numerous labs around the world, that there was more work to be done. There's still more work to be done in moving this young technology forward. Here are some applications for ALD that most of us are familiar with, the displays and batteries and semiconductor work, but there are numerous applications for it. Anywhere where a very thin conformal film that's pinhole free could be used, we can find applications for. So this is a chart of publications per year from 1993 to 2022. So you can see that in 1990, there were only about 20 publications, maybe 30 publications being done. And this is a logarithmic scale. So we're moving closer to 10,000 publications being done as we move into 2021 and 2022. So obviously a huge change in the number of people doing research, the number of labs doing research. But what can we do in order to get even more people on board and move that even further? So ALD chemistries are numerous. This is a database or a screen capture from the Atomic Limits database where they show just how many compounds are available. So the easiest way to read this periodic table is to look for a given parent element, let's say aluminum in cell 13, and you can see from the different colored squares that there are aluminum fluorides capable, aluminum nitrides capable, aluminum oxides, aluminum sulfides, as well as other combinations represented by the black square. Now, within each of these chemistries that you can identify, or within each of these materials, there are numerous chemistries that can be used to get to these materials. And so even just looking at the materials available, there's quite a few that can be done with ALD. There's just applications out there waiting to be found, and there's new materials being found every day. So what were our motivations? Why build another ALD system and put it on the market? First thing we wanted to do was really lower the barrier to entry for ALD research. So as it stands today, when you're getting into or considering as a new lab or as a lab looking to get into ALD, how do you make that leap? Well, you can build your own system, which comes with its own risks, meaning you can have to deal with, are you designing it to carry out the LD process right? Are you building the control system? Your temperature management, all those things that kind of go into building any deposition system. So you have that choice to sort of aim for that hurdle, or you can purchase a system at much larger expense. And is it really going to be flexible enough to handle that? So your options are build it yourself and deal with all the risks associated with that, or with a very high cost, go in and buy a turnkey system and hope that it does the things that you'll need it to do, not only this year and next year, but maybe 5 years from now or 10 years from now as a capital piece of equipment. We also wanted to make our system 3D sample capable. So we'll explain a little bit more why later, but that was sort of a big thing for us. We also wanted it to have a small footprint so that you could bring the system into a lab without having to make huge considerations about where it was going or what equipment to move around or to make it accessible. We wanted to make this very easy to bring into a lab. We also wanted to lower maintenance costs. We have a few strategies for doing that. We then designed it to handle a variety of precursor vessels. As you guys know, with research, it's never necessarily what you think it's going to be, and there's always something coming up. So we want to make sure that the right precursors could always go on the system for whatever the user was intending for their research. And then, because there's no one-size-fits-all system for ALD, we wanted to provide expansion options. We want to provide a base system that can get it going and allow users to do what they need to do, sort of get started, get their foot in the door. But maybe as research changes or research evolves, what do you need to do to keep up or to improve the system? And we wanted to provide options for doing that. So here's a picture of our research ALD system. We really believe it's the most economical 3D capable system on the market today. We also gave it, as you can see, we did succeed in our benchtop footprint. But more than that, we made it user maintainable. We want the users managing maintenance. We don't want to have to trap you into a contract where you only can have a technician come out and maintain the system where something goes wrong. We really want our users to be involved, and not only in maintaining the system, but able to modify the system to support their research down the road. And we also have the system using standard lab utilities. We didn't want you to have to worry about anything special, whether it's the voltage that's going out, how much power you're delivering near the system, or the gases being provided. We wanted that to be all fairly standard and easy for any lab that picks us up, whether it's an academic lab or an industrial lab. To make it a little easier on turnaround and sort of user experience, we gave it a quick access door so that samples can be loaded and unloaded relatively easily. There's no special tools required. There should be no special apparatus required to load and unload samples and get them where they need to be. And then we designed it to accept not only the prepackaged cylinders that you might find from Strem Chemical or Sigma Aldrich, but also refillable precursor cylinders. So if you're working with a organic chemist who is synthesizing precursors for you, you can provide them with a cylinder that can be loaded and unloaded at the completion of their process and then loaded onto the system so that you can continue with your research. So the first thing we did was it has 4 precursor lines. We wanted it to be able to do a couple of chemistries. Rarely is anybody anymore doing a single material deposition, whether it's because you have an adhesion layer or a capping layer, you're doing a graded material, you're doing a nanolamina. There's often reasons to have more than one material being deposited. And so 4 was a good number to start users with so that they could not only have that flexibility of doing multiple materials, but also not so much that it's hard to maintain or hard to deal with and run into issues there. So all 4 lines will accept a prepackaged or usable refillable vessel. We also arranged the lines so that they maintain themselves as far as cleanliness goes. We didn't want the users having to take apart lines when something goes wrong. So we've really tried to minimize it so all the deposition happens just inside the chamber and through the exhaust. That way it's easier to service, it's easier to access, and it doesn't require any sort of specialized equipment to get into those valves or specialized cleaning. We also included user serviceable valves. So we carefully selected our valves to be capable of both being replaced by the user as well as being serviced by the user. Because research, it's often hard to know when things are going to go wrong in research. We wanted to make it easy on the user so that they can service their own valves and get the system back up and running if something does go wrong, if they've overheated valves, if they've introduced a precursor that destroys a valve, anything of that nature. We also included a 200 C upper temperature limit. Currently on the ALD database at Atomic Limits, there are 1,000 ALD materials currently listed. Of those, a very significant portion can be done at under 200 C, and that is including without resorting to plasma enhanced ALD to lower the reaction temperature. So we figured this is a good, reasonable range to give most users to start their research and sort of get a handle on things and cover most applications that folks would be researching at this time. So the fast entry door is nice not only for loading and unloading samples, but it also provides full chamber access. So if you are needing to clean the system or a sample degrades in the system or you shatter a wafer or whatever your sample is inside, it's easier to clean out and easier to access the entire chamber volume. We also gave it a very large chamber volume right now. It's 600 millimeters by a diameter of 125 millimeter usable sort of deposition area. To give you an idea of what that is, this stack of Amazon dots or Alexa dots would actually fit inside our chamber quite easily and be able to be deposited on. Now, while that's a large chamber, not every sample needs that size, or you might be putting many samples in. And one of the things we're offering is custom sample holders to make that easier on our users. So let's take a look at how this system's a little different than turnkey systems. One of the common features around a turnkey system, and if you notice all these images, this is also an image from the Atomic Limits image database, is they're flats. They're designed around wafers. They're designed to handle wafers, whether it's multiple wafers in a batch system, whether it's a spatial ALD system, whether it's sort of the standard flow type thermal ALD systems. They're often designed around flat, large substrates. And that doesn't cover necessarily every application. We wanted to give our users the ability to cover flats as well as three-dimensional. So they're also best serviced by a technician. Rarely is one of the turnkey systems able to be serviced by the end user. Now, that's not necessarily because they were designed that way, but when you have these large, complicated systems that can do a lot and they're designed for production, they're really best serviced by an experienced technician who's been trained and knows how to handle the systems to get the user back up and running as fast as possible. The other thing is these systems can be quite expensive. Most of them don't start until a couple $100,000, and that's just not necessarily a price point that is attractive to somebody, to a lab who's just getting into ALD research and maybe doesn't want to really make that full leap to a production capable system yet. Often they have large footprints. Rarely are they benchtop capable, just because there is a lot that goes into these systems, and it's been the typical design to make it a standalone system. Precursor vessels can also often be expensive. Often precursor vessels are designed solely for that piece of equipment, or that piece of equipment only accepts a specific type of sample or precursor holder so that it can always hold it or heat it or do whatever it needs to do with the sample holder. We've tried to get around that by making our sample vessels, or our precursor vessels, a little more flexible. And also in situ monitoring is fairly rare on ALD systems. There's not usually one that comes with that or has that option available, because monitoring ALD systems is generally difficult. And one more thing about our research system. So we plan on having it be 120 volts, only pulling about 30 amps, which is more than normal in most lab space panels. Uses compressed air, and it uses carrier gases. Those will really be the only connections needed to get this system up and running. And so our goal is to have a system from delivery to up and running in about an hour, which we think is pretty exceptional considering the long times it takes to install most systems. All right. Well, thank you very much. Hopefully you've got a good understanding of what we've tried to accomplish with our research ALD system. If you'd like any more information, please email me at info@max-sci.com, or you can call us at 513-214-1776. And thank you for your time.